Okay, so this will be a super quick video on week 3 examples, which covers a lot of the actual crystals. So a lot of them are silicon based, and I'm just going to jump into a quick couple of examples. Um, number 2 and 3 are they kind of use the same concept, but the number one's a little bit different. So let's just jump straight into it. So number 1 explains, in terms of bonding, explain why silicon materials have relatively low densities. Okay, well, to explain this one, hopefully you see this screen. Well, the reason why silicates tend to have low densities is because if you look at the actual silicates, they tend to form tetrahedras. So just gonna try to draw a tetrahedra over here. They tend to form tetrahedras. So then because of that, once you have multiple of these tetrahedras within one area, what they kind of do is that they kind of bond to each other. They kind of attach to each other like this. And naturally, as we see over here, it'll become more obvious as I stack another one on top. You see how I'm kind of left with just a little bit of space in between these tetrahedras. So if you think about the closed packed nature of, say, a ceramic material, specifically an anionic or a metal material, sorry, can't talk today, you might recall the closed packed structure that a lot of these metals have. And we see how there's very, very, very little room present in between these atoms over here. But then that's not really the case with the silicates because the silicates are based upon the silicate ion. And we see that they form this tetrahedra. And because of the very nature, the geometry of the tetrahedra, and the larger radius of silicon in general, they tend to form these shapes that kind of leave a lot more room in between each other, as opposed to, say, ionic materials or metals, where everything is quite literally close packed. So then that explains why silicate materials tend to have relatively low densities. For number 2, suppose olivine, which is just a type of gemstone, has 200 nesosilicate anions for every 25 magnesium ions. A, how many iron ions, assuming that it's F iron 3, would there be in neutral olivine? Well, neutral is a bit of a not as needed because number 2 and 3 have the same gimmick in that electrical neutrality is the priority here. And what you really want to achieve is some kind of electrical neutrality. So if you go into the general structure of an olivine, it might have some kind of cation, one here, and then was it a second cation over here? Whoops. Second cation. So Ca referring to cations, not calcium. And the nesosilicate anion is just SiO4. And it's important to remember that SiO4, nesosilicate, has a charge of -4, while magnesium always has a charge of +2. And we're given that we have, let me see if I can make this bigger. There it is. No. Okay, whatever. And we're given that we have 200 nesosilicates, so then I'm going to form an equation. So 200 nesosilicates times -4 for the charge, plus 25 because we're given that we have 25 magnesium ions multiplied by 2 because that's the charge of the magnesium, plus X, which represents some number of iron that we have, multiplied by +3 because that's the charge of iron that we're given is equivalent to 0. And if we just do some math, we will get that X is around, and you can round off here, 250. So we have 250 ions of iron 3. So then that's for the first part. For the second part, what will be the values of X and Y, and N and Mg, X, Fey, and SiO4N. So in this case, if you didn't know what the basic structure of nesosil or of olivine would look like, B will kind of be that big hint. And we see over here, what we can do is that we can set a ratio. So taking our answer from part A, we know that the ratio of Mg to Fe to nesosilicate SiO4. I really hope you guys can see this because it is a bit thin. Let me see if I can, no. Oh, well. I don't, can I? Thickness, yes. Okay, a little bit better. And we know based on the ratios that we have 25 atoms, 250 from part A, and 200. And obviously we don't want to put those numbers. So what we'll do is that I'll actually divide by 200. So divide by 200, divide by 200, and divide by 200. And what I get is that I get 1/8, 5/4, and 1. And obviously, I do not want to put fractions. But what I can do is that I can multiply everything by 8. So this gets multiplied by 8. This gets multiplied by 8. And this gets multiplied by 8. And I get 1, 10, and 8. So then I can rewrite this formula as Mg1, but we don't need to write the number there. Fe 10 SiO4 8. And we can double check whether this is right by checking the electrical neutrality. So then Mg, well, that's going to be plus 2 plus 10 because I have 10 atoms of iron 3, so then that's going to be plus 3 plus 8 ions of nesosilicate, which has a charge of -4. And this is going to add up to 32 minus 32, because remember the negative charge over here, this is going to give us 0. And that's exactly what we want. Next part. So diopside is a simple single chain enosilicate containing equal numbers of calcium and magnesium counterions. Propose a formula for this mineral. Okay, well, again, it's very similar in concept to number 2 in that we want to prioritize electrical neutrality. So if we remember the basic structure of an enosilicate, the basic subunit will be SiO3. And this has a charge of -2. I don't know why I drew in those parentheses. Those are not needed. So then continuing there, we know that it has equal numbers of calcium and magnesium. So then calcium has a 2 plus, magnesium is also 2 plus, and enosilicate is 2 negative. And remember, I want electrical neutrality. So what I'll do is that I'll have a ratio of 1 to 1 for the calcium and magnesium. So I'm just going to put 1 atom of calcium, 1 atom of magnesium, but I'm going to put SiO3, enosilicate, in parentheses because I want 2 of them. And this is going to work out quite well because Ca is plus 2, Mg is plus 2 again, and enosilicate is -2, but I have 2 of them. So then this is 2 times -2. So then I get 4 plus -4 is equal to 0, and that's exactly what I want. Alternatively, you can write this as CaMg. I've seen sometimes people write it as Si2O6, same idea. Both are correct. And yeah, this is going to be a very quick video. Hopefully everything made sense. And as always, message me if there's any questions. See ya.